Hello and welcome to the Further Maths Support Programme revision recordings for A-level modules. Today we're going to be looking at Edexcel Mechanics 2 and we're going to be looking at the second part of this, general motion in a straight line. The topics that we're covering for Mechanics 2 altogether are listed here. If you're interested in recordings for revision for any of the other modules, you should find those in the same area as this particular recording. Okay, so this is an excerpt from the specification for Edexcel Mechanics 2 and it shows what you need to know for the general motion in a straight line, which in this particular topic is usually referred to as kinematics. So you need to be able to deal with velocity and acceleration when displacement is a function of time. So we're looking here at variable velocity and variable acceleration. So velocity expressed in the form dx by dt, or a function of t, and acceleration expressed as dv dt, the rate of change of velocity with respect to time, or a function of time, and you will need to use calculus in order to be able to work with those. You'll also need to be able to handle differentiation and integration of a vector with respect to time, so that this is the displacement vector. You would need to be able to differentiate that to be able to find the velocity vector, and differentiate again to be able to find the acceleration vector, etc. So let's take a look at some of the ideas involved in general motion in a straight line. This is what I like to call the calculus ladder for kinematics. You can see here at the top we've got displacement related to velocity related to acceleration. When you move down the ladder, i.e. if you're trying to find velocity from displacement, you need to differentiate. If you're trying to find acceleration from velocity, you need to differentiate with respect to time. If you're moving up the ladder, you're integrating with respect to time. So increase your height, integrate your function. So integrating the acceleration gives you velocity, integrating velocity gives you displacement. Down here in the bottom we've got a cloud of different different terminology for various different sessions, various different variables involved here. I'm going to start with displacement. So all of the things that I'm circling here in red could represent displacement. So x and y could both be displacement. R here is often used where you've got vector displacement. I'm going to put a wiggly line under A here because sometimes A can represent a distance. So I'm going to kind of mention that as a possibility that it can sometimes be acceleration, but it could also be considered as displacement. This vector expression down at the bottom here is also a displacement. That's a position vector of a point. And all of these can be used then to represent various displacements. If I switch colour so that we're dealing now with velocity, if you differentiate displacement with respect to time, you get velocity. So x dot is a velocity. Dx dt and x dot here are exactly the same thing. Both of those are velocities. Here is the vector version of displacement differentiated with respect to time, and here's a 2D vector version of displacement differentiated with respect to time. So all of those expressions can be used to represent velocities. Again, if I switch pen colour now and go to green, looking at acceleration. Acceleration is rate of change of velocity with respect to time, so v dot is one way of, v dot is one way of representing it. V dot and dv dt are exactly the same. Alternatively, you can have a vector version, so dv bar by dt here is the rate of change of a vector velocity with respect to time. And then we've got our second derivatives, second derivative of the displacement vector, second derivative of x, and the second derivative of x with respect to t here. Again, these are the same thing. And of course little a is often used for acceleration as well, although it tends generally to be used for constant acceleration rather than more generally for a variable acceleration. Okay, so let's look at some examples here. We've got a particle p moving on the x-axis. Its acceleration is given by t minus 4 in the positive x direction, and you're given some initial conditions. If you want to do this question yourself at home, if you're playing along, then now's a good time to pause and work through the question because I shall be going through the methods here. Okay, so if we know that dv dt, the acceleration here, is given by t minus 4, in order to find v in terms of t, we're going to have to integrate. I'm going to use a separating the variables method here. If you prefer, you can use constant of integration. So dv on one side and t minus 4 integrated with respect to t on the other side. We know that when t is 0, v is 6, so I can pair up my limits here. V is 6 when t is 0, and I'm looking for a velocity at a general time t. Integrating both sides here, left hand side gives me v between 6 and v, and the right hand side gives me t squared over 2 minus 4t between 0 and t. Putting those limits in on the left hand side gives me v minus 6, and on the right hand side t squared over 2 minus 4t, and then minus zeros, which means that my expression for the velocity at time t is t squared over 2 minus 4t plus 6. As I say, if you prefer, you can do that using constant of integration. You should come out with exactly the same expression. For part B, we're being asked to find the values of t when p is instantaneously at rest, so we're looking at where t squared over 2 minus 4t plus 6 is equal to 0. If we double through there, we end up with the quadratic t squared minus 8t plus 12 is 0, and we can factorise that to give t minus 2, t minus 6 is 0, and so the values of t then when v is 0 are 2 and 6. Okay, and then finally it asks us to find the distance between the 2 points at which p is instantaneously at rest. Well, we've got an expression for v in terms of t. That means we also have an expression for x dx dt, sorry. Okay, so dx dt is the same as v. So dx dt is t squared over 2 minus 4t plus 6. If we want to find x in terms of t, again we need to integrate. So left hand side integrating x dx, sorry, with respect to x, sorry, 1 with respect to x, I'll get there in a minute. That's going to be the integral of t squared over 2 minus 4t plus 6. All of that integrated with respect to t. Again, I'll put my limits in. It tells you that when t equals 0, we're looking then for the distance between the 2 points at which p is instantaneously at rest. So I'm going to make x between 0 and I'm going to call my distance that it travels s, and we know that time's going to do between 2 and 6 from our previous answer. Left hand side is just s, and the right hand side becomes t cubed over 6 minus 2t squared plus 6t between our two limits, 2 up to 6, and we can substitute our values in there. That's going to give me, sorry, lost my thread there for a second. Substituting the 6 in gives me 36 minus 72 plus another 36, and then minus, putting 2 in there is going to give me 8 over 6 plus 8, and then minus 12 in there. That gives us an x value of 16 over 3. The question asked us for the distance between the 2 points. Really, we should be giving that as a positive value. So the distance between those 2 points is 16 over 3 metres in there. Okay, let's take a look at the second example again. Here, if you would like to work through this question yourself, then now is a good time to pause, as I'm going to begin the explanation. We're told in this question here that v is 3t squared minus 4t plus 3, and we're told that when t is 0, p is at the origin O. We have to find the distance of p from O when p is moving with minimum velocity. Now you notice there are 8 marks here for this question, so we're now going to have to do a fairly substantial amount of work. Let's think about when p is moving with minimum velocity. So when p is at a minimum, notice that this velocity here is a quadratic expression. When p is moving with minimum velocity, we're looking at this lowest point here on the curve, and that turning point is found where the gradient is 0, i.e. where the acceleration is 0. So we want to make an expression for dv by dt, the acceleration, equal to 0, so we differentiate. That gives me 6t minus 4 and we're going to make that equal to 0. So 6t minus 4 equals 0 means t equals 2/3. That's the time at which p is moving with minimum velocity. Okay, so we know the time, but we don't know an expression for the distance at the moment. So again, let's go back to our expression for the velocity. This time we're going up the ladder. Here we were differentiating down the ladder. Now we're going to integrate up the ladder. We know that dx dt is equal to 3t squared minus 4t plus 3. And if we integrate both sides of that expression, this time I'm going to do this using constant of integration. So my left hand side becomes x, right hand side becomes t cubed, not over 3, that cancels away, minus 2t squared plus 3t plus my constant. I know that t is 0, p is at the origin, so x equals 0, so t equals 0, x equals 0. I can substitute that into my formula here. That means that 0 equals c, so my constant here is going to be 0. So x equals t cubed minus 2t squared plus 3t, and we can substitute our t equals 2/3 into that expression then to get x equals 8 over 27 minus 8 over 9 plus 2, and that gives me 38 over 27 meters, which is not a particularly chummy number, but there we go. Okay, well, thank you for watching. I hope you found that useful. If you have a moment, I suggest you take a quick look at the Further Maths Support Programme website. It has lots of information about how the Further Maths Support Programme supports schools and supports students, and I hope that you're successful in your examinations. Thank you very much.